as is our practice, we are roughly say a little more than half the class time. So physical break you can take any time. You can pause my lecture and go have some water or tea or whatever. But the mental break time, right? The mental break time. So don't read. We will cover this later on. Again, I am repeating a joke which I very much liked. You may remember it, you may not. But just a little bit of history and geography for you. You know Pakistan. Pakistan has borders with Afghanistan. And Afghanistan has always been a land of the maximum resistance to foreigners. In the 200 years, the English were there in India, Pakistan, and they could never control it. Then the Soviet tried it for 15, 20, 30 years. They were defeated and went back. Now the Americans have been there for 15, 20 years, and they have never been able to really control those. So those people who are in northwestern Pakistan and those people who are in Afghanistan, you call them Afghanis, but they are basically Pathans, right? And their language is also similar and so on. And they are very independent type of people and so on. So they are very strong people, very independent people. Also, I have lived among them for about 3 years. I was teaching at a university in northwestern Pakistan, which is called the GIK Institute. It is a very high level institute, takes very few selected students, Ghulam Ishaq Khan Institute. And that is in the Pathan region. So I really lived with those and I love those people. They are very hospitable. You are passing through, near a house and it is dinner time and they don't know you at all, but they will invite you that please, it is dinner time, come with us and this and that. And they are very religious also. I know I used to travel with them and so on. The bus driver is a Pathan and suddenly there is the time of Asr. And he says that, you see, Asr time is there, I am sorry, I am stopping the bus. And right near the bus, they will have a Jama'ah and so on, and then they will proceed, whether there is a masjid or not. So they are very religious people also. So now back to the joke. That in the Pathan region, there is a masjid, and there is this Khan Sahab. If the last name is Khan, Khan, then he is a Pathan. Right now, for example, the Prime Minister of Pakistan, is Imran Khan. So he is one of the Pathans. But okay, so there is this Khan Sahab and he goes to a masjid regularly. Now, one day, and he's a very decent person, he goes all the time to masjid and so on. And one day after the Jummah prayers are over, he suddenly jumps 2 or 3 rows, goes to the Imam and starts hitting him. Now people suddenly come, Khan Sahab, what are you doing? So they separate them and so on. Oh, Khan Sahab, you are hitting the Imam Sahab. This is such a big sin. What are you doing? He said, no, this Imam Sahab is a very bad person. And he again starts to hit him and so on. People again separate them. Khan Sahab, this is our Imam. What are you saying? He said, did you listen to his khutbah? He said, yes, all of us listened to his khutbah. No, he was saying so bad things all the time. Khan Sahab, we don't know any of the bad things. No, he said that if you feed a poor person, you will get Jannah. And then he again started hitting. Khan Sahab, this is all very nice. Why are you hitting? No, he said something all. He said if there is a old man on the road and he is not seeing very properly, if you help him to cross the road, you will get Jannah. So he said, Khan Sahab, what is the problem? These are so nice things and so on. No, Jannat is the name of my wife. Okay, right? So the break is over. Whether you laughed or you will laugh later on is up to you. So we were talking of ductile to brittle transition. Ductile to brittle transition, right? So it is a combination of low temperatures, high stress states, fast loading rates, high strain rate. And if this is a combination, low temperature and the stresses are high and the strain rates are high, it is impact type of load, then ductile materials start to behave in brittle material. Right? Now, impact testing apparatus, Sharpie impact test, may be used to find temperature range for ductile to brittle transition. Right? So this can be done, right? That there is an impact testing machine and we do the test at different temperatures. Right? The same material, we make many samples and test them at room temperature, a little below, a little below, a little below, a little below, and then we can find the temperature range where it becomes ductile to brittle transition. Example was the sinking of Titanic. Some metals show distinct DBT temperature, that very distinct. For others, the transition occurs over a range of temperature. Do you understand? That for some of the materials, suddenly at one temperature they become ductile to brittle. But on the others, the curve is more gradual. So there is a range of temperature through which the ductile to brittle transition happens. What are the factors affecting this? The alloy composition, the metal, what is the composition of the alloy? What was the heat treatment that we did? What was the manufacturing process? Right? So alloy composition, we will show in the figure that the carbon content, for example, what the percentage of carbon is the alloy composition, right? Now, major design consideration in material selection for cold environment, that DBTT is significantly lower than the operating temperature. Do you understand what we are saying? If we know that the material or the machine or the component that we are going to use will go to very cold environment, it was normally, say, in normal places, but then it will go to Alaska, it will go to Greenland, and it will work there minus 10 degrees, minus 15 degrees. So if we know that that will happen, then we should select a material which has a significantly lower DBTT, ductile to brittle transition temperature, than the operating temperature, right? We should know that the material we are selecting, first of all, does it have a ductile to brittle transition? If it does not have a ductile to brittle transition, then we are okay in a sense. But if this material is a high strength material, but it will change to brittle at certain temperatures, then what is that temperature? So for example, we are going to an atmosphere where the lowest temperature will be minus 10 Celsius. So if I select a material that will have DBTT at minus 20, then this will always be safe, because it will never become totally brittle. Do you understand? So it should have a DBTT which is much lower than the operating temperature where we are going in the cold atmosphere. So this is one of the design criteria if we are going to cold atmospheres and so on. So now we are showing you the same type of graph in a way, but differently. This is the impact energy, this is the temperature. These are FCC metals like copper and nickel. These are high strength materials where the yield strength is much higher. And these are the BCC metals like iron and so on, right? And certain polymers. And this is a ductile to brittle transition temperature, right? Ductile to brittle. But if you see, they start changing here and they finish changing here. So from roughly here to here, there is a range of temperatures. But there can be other materials which go like this and like this and like this. So there is one specific temperature at which they change, right? So this is what we were trying to tell you in the previous slide. Here we have done the same thing. The energy, here it is in foot pounds, the old English units or the current American units, and here it is in joules. So nowadays, if you see, many graphs are very brilliant in this way, that you can draw the same graph, but you can have one type of axis on one side, one type of axis on the other side. So whether you are working in the United States where they still have the inch pound system, or you are working in Europe where they have the SI system, you can use the same graph, right? Similarly, if you see the temperature, here it is in Celsius, here it is in Fahrenheit. So Europe is in Celsius, USA is in Fahrenheit. If you remember, they have always this huge problem. But this one graph will be okay everywhere. So effect of carbon content. So you see, these are different steels, and carbon 0.01%, 0.11%, 0.22, 0.31, 0.4, 0.67%. So these are low carbon steels to very high cast steels, cast irons, because when that, right? So these are different types of steels. So if the percentage of carbon is high, then they are like this. And if the percentage of carbon is low, then they are like this. And if the percentage of carbon is still low, they are like this. So for these two, you see, there is a very specific DBTT. They suddenly change on one temperature. Here, there is a gradual temperature range. Here there is a much bigger gradual temperature range on which this happens. So if this type of data is available, right, so this is very important, that if we know that whatever machinery we are designing is going to face very low temperatures, then we should have this type of data about the materials, the metals, the steels, the steel alloys that we are selecting. If we don't do this, we just select a material of very good hardness and very good yield strength and altimeter strength, and we feel that we have done a very good design. But whenever the temperature goes below their ductile to brittle transition, they become totally brittle, and now fracture can happen at any given time. The next slide is gone. Okay, so it means that we are done with the first part of chapter 1, and we will inshallah continue. So again, right, please try to download Calister on your own. Please make a habit of going through the lecture with understanding before you come to the next lecture, so that you are ready for questions and so on. Because if you leave many lectures together and start revising near the time of the quiz, your performance is not going to be good. Thanks a lot. Ma salama. End of chapter 1A.